Reaction Rates Part 2, Lecture 16. So last time we introduced this idea of chemical kinetics, the speed at which reactions occur, and we talked about the general reason we can relate the change in concentration per unit time as the rate. This time we're going to talk about what we call the rate law. The rate law expresses the relationship in the rate of the reaction to a rate constant and the concentration of the reactants raised to some power. So we're going to move away from this side, these different instantaneous rates versus average rate. But we're going to start talking about a law that will allow us to relate the rate at any time to some constant times the concentration present, where those concentrations are raised to some power. Right? So see the reaction here, AA plus BB goes to CC plus DD. Notice these rate laws are always in relationship to the reactants. So whichever the direction we are heading, we're only paying attention to those reactants. So the rate is going to be equal to some constant. We introduced this idea of a rate constant the last time, times the concentration of A raised to some power, in this case X, times the concentration of B raised to some power Y. Notice that X and Y are not, I repeat, not related to the stoichiometric coefficients little a and little b. Right? They are some other number. They could be the same, but they are not directly related. Right? So then we can talk about what we call the order of these reactions with respect to a single reactant or overall. So we would say that this reaction is xth order with respect to A, yth order with respect to B, and x plus y order overall. So we can talk about each individual reactant having a certain order, or the overall reaction having an order, where the overall order is the sum of those individual orders. So when we talk about the rate law, it's always going to have this form. The rate is equal to the rate constant, K, or some numerical value of that, times the reactants raised to some power. One thing to note is these rate laws are always determined experimentally. We'll talk later at the end of the chapter about proposing mechanisms to explain these rate laws, but these rate laws are always determined experimentally. So there's no way we can look at a reaction and automatically predict its rate law. We have to do some experimentation to determine the rate law. And we'll look at two different ways to take experimental data and get information about these rate laws. And as we said already, the rate laws are always defined in terms of reactants and their reactant concentrations. And again, the rate order for each reactant is in no way related to the stoichiometric coefficient in the balanced reaction. Right? They may actually be numerically the same, but they are not directly related. Right? In the overall reaction. We'll talk later that in some cases where they might be. So let's go about looking at the first way we can determine these rates or these rate laws. So what we're going to do is we're going to do a chemical reaction. So we're going to look at fluorine reacting with this chlorate or chlorine dioxide to form fluorine or monofluorochlorate. And in general, the rate of this reaction is going to be the rate is equal to some rate constant K times the concentration of fluorine raised to some power times the concentration of the ClO2 raised to some other power. And what we're going to do experimentally is we're going to take a certain concentration of the fluoride and a certain concentration of the ClO2, measure the rate. Keep one of those concentrations the same, change the other one, measure its rate. At the end, we're going to go back and so we're always holding one concentration between two experiments the same, changing the other one. Falls, again, our scientific method, we only change one variable at a time and measure its corresponding effect on the rate. So if we look at this data, right, so this is what we've done. We've taken the concentration and changed it for fluorine, or kept the same concentration of the ClO2 and measured the rate. So if we look at experiments 1 and 2, right, then we see that this F2 concentration has remained constant, right, over here. And at the same time, the ClO2 concentration went up by a factor of 4, or quadrupled. Right? And we see that that's going to have, then the rate has a similar effect, that the rate also quadrupled. So what value of 4 do we have to raise 4 to get 4? And that is 1. So we say that this is first order then with respect to ClO2. If we look at the inverse, where we look at the other one where the ClO2 is remaining constant, and we've changed F2, that's in experiments 1 and 3. Right? ClO2 is 0.01 in both cases, and the F2 went from 0.1 to 0.2. And we see that concentration doubled, and which leads us to get a doubling in the concentration, or the rate. So again, what factor do we have to raise 1 to get 1, and that answer, or 2, what factor do we have to raise 2 to get 2, and that value is 1. So we get the overall rate constant listed here, where the rate is equal to some rate constant times F2 to the first power times constant ClO2 to the first power. So this would be first power with respect to both of these, but second order overall. We can go then further and actually calculate the value of this rate constant by looking at any of these reactions, put in the concentrations, we know the rate, then the only unknown we have would be this rate constant. So in all of these experimentals where we change one variable at a time, what we're doing is setting up a ratio. Right? The rate of reaction in one experiment versus the rate of the reaction in the second experiment has to be equal to the rate law, K times the concentration of each of those raised to some power, and then we're solving for those powers, right? Where half of it was going to remain constant, so it's going to cancel out. So we're going to get only a difference affecting the rate is going to be the change in concentration of one of those. Right? We'll also see that this may not work out easily as it did here. Right? We may have to use the rules of logs to calculate what these actual orders are. Right? We'll also see that if we do these, our orders may not necessarily be whole numbers. We're going to talk primarily in the text and in class and a lot of the examples where we have whole number orders. But that's not always the case. Remember, these orders and rate laws are determined experimentally, and life doesn't always work out in whole numbers. So we're going to see that because of this rule of laws, we can have orders that aren't necessarily whole numbers. For simply discussion, primarily we're going to focus on those whole number values. If we look at the rate constants, typically the rate constant is going to be, the units on the rate constant is going to be liters over moles raised to some overall order minus 1 divided by some unit of time. So if we look at a zero order reaction, then we're just going to have moles per liter times seconds. For first order, the moles are going to cancel out, or that's going to end up going to 1. So we're going to get 1 over seconds. Second order, we get liters divided by moles times seconds. And third order, liters squared divided by moles squared times seconds. But all of them are going to follow this general order where we take liters divided by moles times the order minus 1 divided by some unit t. So we can, once we have this proposed rate law, the k's are actually pretty easy to solve. We just took one of those examples, plug in the numbers, out will pop our value of k, and the orders are just dependent on the overall reaction order.
Dad, I done did it.